Okay, there's been a lot of talk about MPLS as multi-protocol. You think of that multi-protocol MPLS as being layer 3 protocols. Really, only layer 3 protocols carried is IP. There's no talk about doing, for example, AppleTalk or IPX over MPLS. My name is Jeremy Brayley. I'm with Laurel Networks. I'm going to talk about a new application that some service providers are interested in, and that's the carriage of layer 2 frames, technology like ATM, frame relay, and long-haul Ethernet over an MPLS network. This will be our agenda for this morning. We'll have a little short introduction about MPLS and what features are applicable to the carriage of layer 2 services over MPLS, and we'll talk about some of the service provider requirements and why they're interested in this technology. We'll walk through an example of provisioning a layer 2 service over MPLS, and we'll take a look at some of the signaling mechanisms that go on behind the scenes. And we'll close with take a look at some of the layer 2 encapsulations, taking frame relay and ATM AALS and Ethernet encapsulating into the MPLS packet for transport across an IP MPLS backbone. We'll also take a look at some future work to be done in this area. If I could sum up MPLS, I'd call it an efficient tunneling mechanism, but one with an IP control plane. There are a few mechanisms that are especially interesting to us to carry layer 2 frames over MPLS. The first is a separation of the control and the forwarding planes in the network. This allows me to take any type of packet, whether it be IP, non-IP, put a label on front or a set of labels, and intermediate devices called label switch routers will forward this across an MPLS backbone without any awareness of the packet itself. I do not look into the content of that packet. Also, I have this nice label stacking ability. If you think of comparably an ATM service where I have a virtual channel identifiers, and I put these virtual channel identifiers into a virtual path. The same thing happens with MPLS, although this label stacking ability allows me to do this very efficiently into any depth. So that becomes very useful for scalability in the core of an IP MPLS network. The first real application of MPLS was IP traffic engineering. Although IP traffic engineering allows a carrier to increase its operational efficiency by hopefully balancing traffic on its long-haul capacity and decreasing the cost per bit transferred, it does not bring any new services or new revenues to the MPLS or IP MPLS network. Simply, if I can build a tunnel from end to end, I can insert layer 2 services, layer 2 connections into that tunnel, and the core manages a far fewer number of connections. In the same vein, there's ease of provisioning because I only have to touch the edge devices. All my service creation is done at the edge of the network rather than in the core. The core remains blissfully unaware of any services it is carrying. There are a few methods of providing layer 2 services over MPLS being worked on in the IETF today. The first I'll call MPLS-based layer 2 VPNs. This is based on a draft by Kriti Compella of Juniper Networks. Dr. Compella spoke at the previous NANOG, so I won't go into too much detail about this particular method. Suffice it to say, this is a method of easing the provisioning problem of full mesh VPNs. It means if I have a full mesh of n sites, I need n squared connections to the core, and that's a lot of connections to manage, especially as n grows large. The next pair of drafts are layer 2 transport. This is written by or authored by Luca Martini of Level 3, and not so coincidentally by a few members of my company. It defines two drafts. The first is transport in a signaling mechanism using LDP, Label Distribution Protocol, in Downstream Unsolicited mode. The second draft defines all the encapsulations necessary for carrying layer 2 frames inside MPLS. So both of these drafts, both these mechanisms use label stacking or hierarchical tunneling in the core. This diagram is meant to show that tunneling mechanism. Here you see on the left-hand side I have a PE device. He has a loopback address 1.1.1.1, and the right-hand side is PE2, loopback 2.2.2.2. The green bar represents a tunnel between these two provider edge devices. The core P devices only operate on that tunnel. If I want to create services over that tunnel, I have a second layer of labels I call the virtual connection, or the VC label, that I insert into those labels. And once I've done that, these dotted lines show the actual connections going to the core. but the core devices are unaware of those connections. If there's a failure or a reroute happening in the core, I do not have to reroute every single connection through that core. We'll talk a little bit about the Martini method once again. In the Martini method, all services, whether they be an Ethernet VLAN service, point-to-point VLANs, whether they be frame relay DLCIs or ATM VCIs, they look like a virtual circuit to the MPLS network. I'll provision each service by associating a port and some type of virtual channel identifier to a VCID. For example, at the bottom of the screen here you see a frame relay service. I take an ingress port in DLCI and I associate it with a VCID. The egress port, I'll associate it to the same VCID. Therefore, they're implicitly mapped. This allows us a degree of separation, so I don't associate the ports directly to each other, and it allows me some flexibility when dealing with moves, adds, and changes for the service. And once I've created that binding, the network is going to discover the tunnel label and the VC label to apply to the packet to get across the network. Okay, we'll walk through an example of provisioning, for example, a long-haul Ethernet service. This is a VLAN service, point-to-point, that I'll offer a customer. Look at PE1, I'm going to associate port 1A VLAN ID 100 to the remote device PE2, 1B 200. The first step is actually have a tunnel created between those sites. And you'll have to do that ahead of time. It could be using a tunneling mechanism, a signaling protocol like RSVP-TE or Sierra LDP or LDP itself. The next step is to create an indirect LDP session. We'll be using LDP to signal the VC labels we'll need to get connectivity across the core. Next step is to look at PE1 and provision the connection of binding between port 1A VLAN ID 100 and the remote peer designated by its router ID or its loopback address 2.2.2.2, and we're going to assign a unique VCID unique to this pair of edge devices. VCID of 50 we'll pick. And on the remote device, provision again a similar connection between port 1B VLAN ID 200 to the remote peer 1.1.1.1 and the same VCID of 50. Once we've done this, our provisioning process is done. It's up to LDP now to create the appropriate bindings in the edge devices. The first step is for LDP process on PE1 to advertise the binding. It picks a label from its available labels. It picks label 500 in this case and advertises a binding between VCID 50 and label 500. Similarly, PE2 will advertise a binding between label 501 and VCID 50. The final step is for PE1 to look into this routing table and discover the appropriate tunnel that it needs to get to remote device 2.2.2.2. It sees here that it can use 600 to go out to that remote device, so it puts on that pair of labels, 600 and the VC label being 501, takes the original Ethernet packet and ships it across this tunnel. Similarly, P device 2 will be choosing label 601 as its tunnel label and 500 as its VC label. And finally, the connection is established across the core. Let's take a look at LDP in review. We're using LDP just for that VC label signaling. We're going to define a new forwarding equivalent class element. Most of the times you see LDP effects as being an IP prefix. In this case, it's going to be a VCID. We'll advertise a binding between that VCID and a particular label of our choice. We'll also need a few extra components of this LDP message, and that's a local port identifier. Helps you ease manageability or troubleshooting of the service, and also a VC type, because we don't want to connect a frame relay to an Ethernet service, for example, by mistake. A little talk about tunnel creation and selection. It plays a large role in what type of service you're offering to your customer. I could create that outer tunnel in a variety of manners. One way would be to use CRLDP or RSVP-TE to create a traffic engineered tunnel, assign some bandwidth, some resources to that tunnel. I could also use LDP for simply provisioning very simply between those two endpoints without applying any bandwidth constraints or any traffic engineering. LDP is also used as a pseudo-signaling mechanism to indicate the status of a layer 2 connection. In this example, we have a frame relay service linking DLCI 100 on PE1 to DLCI 200 on PE2. Everything's up and operational. Now PE device 1 notices that there's a loss of signal or some type of, perhaps an LMI message coming and status message saying that this PDC is down. The first step is for PE1 to withdraw the label it previously advertised for VCID 50. It's going to send that message over to PE2. PE2 now has to destroy the binding it originally had for DLCI 200 to that VCID, and it's lost that label. So any frames it receives on DLCI 200 has to discard or drop on the floor. Another step is to use that as a signaling mechanism and send the appropriate status message out towards on DLCI 200. In this case, we're using LMI to denote an inactive PVC. If this is an ATM service, I may use an F5 OAM cell, send an AIS out towards the customer. And the final step is to declare that particular VCID down and send the appropriate alarm message to the OSS. Okay, we'll talk a little bit about layer 2 encapsulations. Here you see the complete list of layer 2 frames that we can transfer using this technology. Frame relay, Ethernet, AL5. ATM has two modes, AL5 and ATM cell, as well as PPP, or what's known as Cisco HPLC. Taking the frame relay example, at the top here you see a frame relay frame. The white areas show the address. The DLCI field includes the DLCI plus some of the control bits, the second and the beckon, and the FCS. Both of these fields are discarded prior to insertion into the tunnel. We're going to take that original frame relay PDU and we're going to insert something we call the control word. The control word is useful, it's shown at the bottom here. It contains a sequence number, a length field, and some flag bits. In this case, since we're not transferring the actual address field, we'll need to still carry those beckon, feckin, discard eligibility, and the command response bits from the frame relay header. We'll talk a little more about the control word later in the presentation. Here we show a particular Ethernet frame, Ethernet encapsulation. An Ethernet type 2 frame. I could also use 802.1q if I want to provide some type of channelization on this port. I'll take the entire frame minus any preambles and also the FCS in this case and insert it into the MPLS packet. I will not use the control word in this case because I am sending the VLAN ID and the original MAC address information along with the packet. The VLAN ID itself may have been rewritten at egress. Give me some flexibility there. And I prepend my VC label and my tunnel label to the packet before sending it out. It should be noted that if these particular PE devices are adjacent and you're using something called penultimate hot popping, you will not need that tunnel label. You can simply use the VC label. Again, there are two types of ATM encapsulation used. The first, we're trying to emulate a frame service or an AL5 service over MPLS. In this case, I take the entire AL5 PDU. There is an 8-byte trailer in ATM AL5 that I will discard. That contains the FCS. It also has some control bits. We are interested in one particular control bit, and that comes from the UU octet, and it's used to carry frame relay's CR bit in the case of frame relay FRF8 service interworking. So we'll take that one along with the T bit is the type, distinguishes between our AL5 encapsulation and our ATM cell mode, which we'll talk about next. I do not include any information regarding the address or the VPI VCI for this connection. Again, the EFCI is interesting to transfer the CLP bits and that CR bit. The ATM cell mode is an interesting encapsulation. The idea is, as opposed to the AL5 mode, we won't be doing any segmentation and reassembly on ingress. But the idea is to carry ATM cells over an MPLS backbone, hopefully a higher speed MPLS backbone, one operating at OC192C, which most ATM switches do not quite support at the moment. In this case, we're taking the original 53-byte cell. We're going to take off that FCS bit because we already have an FCS, hopefully, in the frame, in the layer 2 frame, we'll actually be going over. The control word is optional. Again, it contains a sequence number, and the length could be used to designate the number of cells that I'm encapsulating in this particular frame. Let's take another look at the control word. In review, the control word, its original purpose, there's been some controversy concerning the control word actually, because we want to include the sequence number, and this has been something that's been relatively difficult to do. The purpose of the sequence number is to use that sequence number and increment it on ingress, but then use it to detect out of order frame delivery on egress. Services like frame relay and ATM actually require you to keep your sequence numbers intact or keep sequentiality through the core. The length field is used in case you want to pad if you have a particular frame that's smaller than, say, if I'm going over an MPLS length that happens to be gigabit Ethernet, for example, and it has a minimum frame size, or Ethernet minimum frame size. And the flags we've seen examples of before, using the FEC and the BEC and the ESCI and the various control bits. Finally, I'll talk a little bit about class of service considerations. I don't want to talk in detail about class of service, but there's been some interest in providing at least very coarse-grained prioritization in the backbone. If I'm offering an internet service, for example, I may choose to mark it a certain way, and if I'm offering a frame relay or a layer 2 service, I may want to give it a higher prioritization. I can do this using some of the diffserv over MPLS drafts. In other words, I'm taking that EXP, the experimental 3 bits, I'm going to mark them in a certain way when I send these packets over the tunnel. The provider devices will respect those EXP mappings and will priority queue them appropriately. Most core routers support at least 4 queues on the interface and can do this type of prioritization. Similarly, if I'm going to even think about doing 802.1p and providing that service, I'll need all 8 values of those EXP bits to transfer across the core. And finally, some future work. The most interesting things at the moment have been interworking for this service. There's been some interest, obviously, in doing frame relay, ATM interworking, service interworking a la FRF8. This is interworking between inverse ARP and ATM and frame relay inverse ARP, as well as doing the mapping between OEM cells and LMI status messages. There's been relatively new interest in connecting a user, perhaps who's running Ethernet on one side and actually frame relay on the other side. I can do some measure of IP interworking. This is a very early stage, and we'll see if that's a good idea as we move forward. Finally, SLA measurement. If we're going to offer layer 2 services over an MPLS network, we need an analogous method of doing SLAs and some improvements in the way we do our OAM and adding things like continuity check to this service. In summary, I want you to begin to think of MPLS as more of a service-enabling technology. It's not just for traffic engineering anymore. And you see how the scalability of MPLS plays a role here. I can have far fewer number of connections to manage in the core, and I've migrated my services from the core of the network to the edge. Are there any questions? I see a question back there.
Hi, Bill Nicholas from Argonne. I talked on multicast yesterday.
Okay.
My question does revolve around multicast. I was working with a service provider not too long ago who had an ATM core where they had a bunch of ATM VCs connecting all their core routers. The problem with that strategy in multicast is that you do all the packet replication when you enter the core, which means your links are unnecessarily oversubscribed. One can make that argument. Is there any work in the MPLS community to try to address this problem of replication where necessary, rather than causing each of the edge switches to do the packet replication and oversubscribe the core?
I'm not aware of any work. My expertise is not in multicast, actually, but I'm not aware of any work in MPLS to do that.
Yeah, that's worrisome if MPLS isn't architected to support that service,
well,
to me.
One of the examples is we would do MPLS and IP. I think they'll coexist for some time. If you want to do multicast, most core devices some of the largest core routers support both MPLS and IP. I'd imagine you could use MPLS tunnels for certain service applications, point-to-point applications, and then use regular IP forwarding for some of the reverse path forwarding algorithms and sparse mode algorithms.
But doesn't that reduce your ability to do traffic engineering in that situation?
Traffic engineering for
Traffic
multicast?
engineering for the IP services, doesn't that eliminate one of the advantages of MPLS?
Well, you have some control. Well, don't want to talk too much about traffic engineering applications because there's other people that could do that. But you have some flexibility here. I can use, just by controlling things like administrative distance. Cisco has an administrative distance command. Juniper calls it preference. So another question here? Yeah.
So how many routers in a relatively large network do you have to convert over to understanding MPLS in order to do these services at the edge compared to what Peter Lothberg was talking about yesterday?
Okay. Well, what I've talked about here compared to what Peter Lothberg talked about yesterday, and if I understand his presentation, he was advocating using IP tunnels, or something he called UTI, which I wasn't familiar with. Certainly, this is an alternative to doing something like that. What I've shown here already isn't very complicated, the LDP signaling. We're not doing any traffic engineering. There's no new routing protocols to learn. LDP itself is very, very simple. To do a layer 2 service using this mechanism, I don't even have to learn anything like BGP if I'm providing a layer 2 service. So hopefully it's easy to understand and provides a simple tunneling mechanism without all the complexity of doing traffic engineering. Did that answer your question there? Okay. Okay, thank you.